Okay, so we're going to talk about FEA operations today and how this goes together. So, just starting out with a simple one-dimensional spring system to kind of get us oriented, learn how this goes, and put it together. So our U's are our node displacement, and they can be in whatever units we choose, right? So in our node is depicted by a 1, 2, or a 3. A number inside of a circle is going to indicate a node. And then we have elements, which are going to be in squares. And we have 2 elements and 3 nodes connecting it all together. Our F force is attached to node 3. Okay, and then when we refer to these, this is going to be, we refer to the node and then the element. So 1, 1, 2, 1, 2, 2, 3, 2 would be the way that we refer to those. So when we put our equilibrium equation together, right, we want it to balance to 0. We have our internal force, our spring constant, and our displacement of our 2 nodes. And we're going to assume, to begin with, that we have positive displacement. So if we solve for the internal force, then we're going to get those equations, right? Basic algebra. And so we have FIP, so node I, element P, JP, node J, element P. So that's how we're putting it together. Okay, so if we put it in matrix form, right? Remember, we're doing K times UI minus K times UJ is going to equal FIP. And we do the minus because it's an internal force. So if we do the matrix algebra, you're going to end up with these equations. Right? Everybody see that from the practice we've been doing with linear algebra? Okay. So if we want to put it in a general form, then we're going to say KD equals F. K being our element stiffness matrix, D is our displacement vector, and F is our internal force. So it kind of looks like F equals KS, right? Our spring equation. So let's put our system of equations together here and begin to try to solve for the displacements. So at element for element 1, right, if we put our matrix together, we're going to have these equations for element 1. This one related to node 1, this one related to node 2. Same thing for the second element in matrix form. And then when we put it together in an equation, so this is node 2, element 2, the third node, and element 2. Is that making sense? Okay. So we go another step. So we take our general, or our equilibrium, right? Internal force has to equal the external force. So this would be at node 1, node 2, node 3. And if we substitute this F11, remember our equation for that was K1U1 minus K1U2. So our displacement at 1 and 2, our spring element constant 1. At this location, or this node, right, we have the force from element 1 and the force from element 2, or the spring force, right? And for node 3, we just have this. So if we put it together, if we take our equations, put it in the matrix form, or even define it as general, this is what it's going to look like. Is that making sense so far? No. Where are we starting?
How can you have K1 and K1 on the top row? Wouldn't they have to combine to the top left cell of the meters?
Well, this equals
Right.
that.
I get that. The whole K1 thing goes further because it seems like it should be combined.
Well, this K1 is element 1 spring constant. And this is still element 1 spring constant. This is the displacement at node 1. And this is the displacement at node 2. Okay. This equation, or this F, equates to this guy. And this one equates to that guy.
I see no matrix expression I use as a K, so it's
Yeah. Okay, no problem.
what
No, because you have to be able to follow through, because we're going to do some example problems that that work through this. So we've got our system of equation, and we've got things set up and ready to go. So now, so these are our loads, these are our equations. Okay, so now this is our matrix form of our system of equations. So let's talk about boundary conditions now. Okay, so we figured out what our equations for the deflection of the nodes and what those are. So now let's look at boundary conditions. Well, U1 equates to node 1. Are we going to have any deflection at this location? No, because it's attached to the wall, right? We consider this a rigid body, and so there's not going to be any movement there. So this becomes 0. Okay. Do we have any forces at 1? No, no forces either. So this is going to go to 0. What else? We don't have any forces at 2, right? So that'll go to 0. We will have deflection at 2 and 3, and we have a force at 3. So let's see. Okay. So what's going to happen to this equation now that I've put these zeros in? It's going to simplify. What's going to go away over here? The whole top row is going to go away, right? I mean, initially doing our matrix calculation, this times 0 is going to equal 0, but because this is 0, these also have to equal 0, right? So the whole top row goes away. So we're left with, well, this is 0, right? This force is 0. So aren't all these going to have to equal 0? No, because we have some displacement there. So now this should be my corrected, or no, it's just got the zeros in it. Okay, so there's our simplified. So now we're down to 2 equations, right? Is that making sense? So what's left? So now what we can do is, once we know, or well, we should know what this K is, what's this spring constant, we can plug it in here. And we should know what this force is, so we can plug it in here. So we know what the K's are, and we know what our forces are, so we can solve for our U's, right, for what our displacements are. So that'll tell us how much these deflect. So we can, if we had a more complicated system, Obviously, our system of equations would be bigger and more complicated, but it would set us up. And, I mean, we can use this simple one-dimensional spring simulation to approximate some real forces and a real application just by, we're going to break this into two nodes and say this is one element, this is one element, and we can use this to determine how much that's going to deflect, right? And we can write our system of equations to be able to figure out how much node 2 is going to move. Same thing for this one. We can represent this real scenario with this one-dimensional spring setup, write up our equations, and away we go. And we can solve for that solution for those displacements. So sounds simple enough, right? So another way that we represent the real world, if we were trying to calculate the deflection in this tapered shape with our analog calculations, it would be very difficult. So if we break it up into pieces, call it squares, approximate it, right? Then again, we can use a spring representation to determine what those deflections are going to be. So this is leading up to, we're going to create representations of our geometry to be able to solve for our finite displacements. So questions about that? Okay, so we now have the building blocks and understand the equations behind what's moving these nodes around, right? And it would, for something even of this size, it would just be a much bigger set of equations that you have to solve for simultaneously, and that's why we do it with the computer instead of doing it by hand, right? Because who wants to sit and do addition and subtraction all day and potentially mess up, make an error. So let's try a couple examples here and see if we can work through this, right? So we have given a one-dimensional spring element, and we need to find the structural stiffness matrix, boundary conditions, and resulting system of equations. So let's do our general formulation, right? So for element 1, right, what's our general formulation? It's K1 minus K1 minus K1 plus K1, right? So this is my stiffness matrix for that. So U1, U2 equals minus F node 1, element 1, node 2, element 1. Right, so that's our general equation. Element 2 okay, it's going to look exactly the same, right? Except for this is going to be U2 and U3, right? F2, F2, 3. Okay, questions about that? Okay, so our equilibrium. Right, we said at node 1, we've got minus what? F11 equals F1. At node 2, oops. So what should I write here at node 2? So I'm at this location. So I'm going to have 2, 1 and 2, 2. Excellent. And at node 3, it's going to be minus what? 3, 2, F2. So I can write a little lower here. Okay, so now we can build our structure of equations. All right. So F11 is represented by what? K1 U1 minus K1 U2. And that's going to equal F1. Here we have minus, let's see, 2, 1. So K1 U1, right, plus K1 U2 plus K2 U2 minus K2 U3 equals F2. Okay, does that make sense to everybody? All right, because we're doing 2, 1, so K1 U1, K1 U2 equals 2, 1, and the other one 2, 2, K2 U2 minus K2 U3 equals that. Is that making sense? And our last one, so minus K2 U2 plus K2 U3 equals F3. So that's our structure of equations. So if we set up our stiffness matrix, yes.
Because at node 1 it's negative F11, wouldn't that change the signs on structure equations?
These?
Yeah.
Well, we're taking this and substituting in that. So this equals that. So no, it doesn't change the signs. Okay. So now here, right, we have K1 minus K1, 0, minus K1, K2, minus K2, 0, plus K2. U1, U2, U3. Okay, so is this making sense? Right? I have K1s in this position. And I have a minus K1 and then 0. We have a minus K1 to U1. I have 2 Ks for U2, so K1 plus K2. And I have a minus K2 for U3, right, because this is going to multiply to here, right? This is a, what, we've got a 3 by 3, and this is a 3 by 1. So those match, so we're okay. And this is going to be a 3 by 1 matrix, right? So here I have a 0, a minus K2 to U2, and a K2 to U3. So minus K2, whoops, this is a Yep, that's K2. So is this stiffness matrix making sense from these equations? Kind of, sort of, hopefully.
This means that not 3 minus F 3 to equal is F 3.
Oh, yes, sorry, thank you very much. Yep, that's a 3. Excellent. Okay, so we have our stiffness matrix. So what's next? So now we can consider our boundary conditions, right? Because we have our system of equations set up. So what can we say, or what do we know our boundary conditions are? What's going to happen here? We're going to have 0 deflection, right? Because we're attached to a rigid body. So that's going to go to 0. And we don't have any force there, so that's going to go to 0. U2, we should have some sort of deflection there. And we have a force. U3, again, rigid body. And no force. So what's going to happen to this row? It's going to go to 0. This row, it's going to go to 0, right? Because our force is 0, or yeah, because we have no force there, so it has to equal 0. So we're left with what? Minus K1 plus K2 minus K2 U2 equals F2, right? So, oh, let's see, we're missing, oh, well, what else? We're missing a couple of zeros here. I forgot 2, right? This is going to go to U1, and that's going to go to U3, right? So those will go to 0, 2. So we're left with K1 plus K2 times U2 equals F2. So now we can solve that, right? Because we should know what our spring constant is, and we know what load we put on it, and we can solve for U. So let's do that. Let's see, we'll say K1 equals 100 pound-inches, K2 equals 200 pound-inches, F2 is going to equal 150 pounds. So we have what? 100 plus 200 equals 150. So U2 equals 150 divided by 300. This is pounds, pound, inches. So U2 equals 0.5 inches. Questions? Does that make sense? Everybody's an expert? Ready to do one on your own? Let's try another one. Okay, so I'm gonna erase this. Okay, so we'll try this one. Let's see, I'll leave those up. Okay. So let's see, do those stay the same element? Let's see, node 1, 1, 2, 1, yeah, 2, yeah, most of it stays the same. So, all right, so now we're going to add a third element, right? So what's my stiffness matrix going to look like? What should I write in there? For the third one, yeah. Just this part right here. Well, what did we do here? So this is element 1, this is element 2. So this is going to be what? K3 and 3, right? So this is K, this is just the stiffness matrix, right? So now what are my nodes going to be? What's connected to element 3? Node 2 and node 3. So my internal force is going to be what? 2, 3, and 3, 3. Is that starting to connect? Make sense? So let's do equilibrium. All right, so at node 1, what do we got? Minus F 1, 1, yep. And what else do we have at node 1? So node 1, which element? 2 equals F1, right? At node 2, we have what? Minus F. So node 2, which elements are touching node 2? 1 minus what? 2, 2 minus 2, 3, right? So then at node 3, we have what? Minus, what's going on at node 3? 3, 3, right? Does that make sense? Right? We're looking at the node and figuring out which elements are touching that node and creating this, our equilibrium equations. Because these internal forces have to equal whatever's going on externally, right? Is that making sense? Okay. So let's see. So now we can do our structure equations. I guess I can do stiffness underneath that, and then, okay, so our equations, right? So what's that going to look like? F11,
K1U1 minus K1U2.
Yep.
Minus
so then we're going to have this value, 1, 2, right?
minus K1U1.
Did I write? I wrote this wrong. Did I write that right? 1, I don't have it. This is the 1, 2. What is this? Where am I? Node 1. So this is a, what is 1, 2? Where's my 1, 2?
It should have been 1, 2, we're doing 2, 1.
Oh, I got it backwards up here. There we go. Okay, so this is then going to be what? Minus K1 U1 plus K1 U2, right? Okay, so now we're down here. So this should have been a, no, yes. So this should have been 1, 2, not 2, 1, right? No, it can't be. Node 2, element 1, so it's a 2, 1. Why don't I have a 2, 1 up there? This is a 2, 1. Yeah. This is gotta be 2, 1. And this is 2, 1. Okay. Have to be very meticulous when we're doing this.
So it
Easily
is it
confused.
node then element or element then node?
Node, then element. Always node, element.
But it should be 1, 2.
No, yeah, it should be, shouldn't it? So they should all be 1, 2s. Yes?
Yeah.
Yes. Okay, holy cow. Sorry. 2, 1.
No. You said one's gotta be
1, 2. 1, 2. Okay, 1, 2. We can count. My apologies. Okay, we got it straight. Node, then element. Always. Node, then element. Okay, so I got, yes, so that's right. So now I'm starting out with 1, 2, right? So 1, 2 is going to be minus K1 U1 plus K1 U2. 2, 2 is plus K2 U2 minus K2 U3. And 2, 3 is minus K, where am I at? 2 U2 plus K2 U3. Okay, did I get that right? I hope. Equals F1 equals F2. So then, what's my F33 gonna be? Minus K, what? K3 U2 plus K3 U3 equals F3. Yes, sir.
At element 2, shouldn't there be a negative F2, 1, a negative F2, 2, and a negative F2, 3?
Element
next to all
2.
3.
Well, okay, element 2
Right.
is here, and I mean, I know we have these dots here, and that's what we want to represent,
Okay.
but the element 2 actually only connects to this node and this node. It doesn't connect to this node. Does that help or no? Am I answering your question?
Oh,
Was that not your question? Everybody else doing okay? Or they got the same questions? Because if you got to be able to do this, because you're going to have homework problems that require you to do this. So if you're not sure, let me know. Okay, let's see. So now we're going to do our structural stiffness or our matrix, right? So what am I going to have for that? got two K1s minus K1. We have a minus K2. Oh, wait a minute. That's supposed to be a 1. I'm going to forget what that is. Okay, so nope. This is a K. Yeah, that's right. So now we have a minus K1 plus K1. Let's see. This is a U1. And we have one U1. 1, 2, K1 plus K2. That doesn't look right. We're missing, this is a K3. There we go. That's what I was looking for. And let's see, that's U2, and then I should have a plus K3. And then what we got here? Minus K3 plus K3. Okay, does that make sense? Let's make sure I got it right. Q1. This is supposed to be a K2 minus K1. Man, I was not very meticulous. Minus K1 minus K2 here. That's right. That's minus. That's. Oh, this one's supposed to be over here. Minus K3. Okay. That's right. Minus K1, Q2 plus. This is a minus. K2, U2, K. Let's go backwards. Plus K3 minus. So that's all right. Those are right. And that's a plus. And that's a minus. Okay. Other than screwing up my signs, we got the right values up there. So, we're at our stiffness matrix. So now is the point where we start talking about our boundary conditions. So what do we have for boundary conditions at node 1? We're going to have no deflection at node 1, right? So we can make that go to 0. And we have no force there as well. Node 2 will have deflection, and there is a force. And node 3 will have no deflection, and there's no force. Right? So that's a 0. That's a 0. Let's see. This is a 0, and this is a 0. So this row is going to go to 0, right? Oh, that's not what I wanted, but okay. So this force is 0. These go to 0. This times that is going to be a 0. This times that is going to be a 0. And these guys go to 0 too. That makes sense? Okay, so what are we left with? I think we can erase this. So what do we got? K1 plus K2 plus K3 times U equals F2, right? So that should be it, right? So now we can solve for what our displacement is, right? If we know what K1 is, what's K1? 100, K2 equals 200, K3 equals 300, F2 equals 150 again. So this is pounds per inch. So 100 plus 200 plus 300 times 2 equals 150 divided by 600 equals 0.25. So now, what if we want to figure out what the force is in each one of those springs? F equals Ks, or say Ku, right? Because we're looking at the displacement. So for force in spring 1, what? K1 is 100 pounds per inch. Our displacement was a 1/4 inch. So 25 pounds, right? F spring 2, and on it goes. Because our deflection, we only have the one deflection. That doesn't look very much like a 5. Okay, so that'll give us the force in each one of the springs based on that. So you have to be very meticulous, keeping track of your 1s and your Ks and all that. Obviously, I didn't do a very good job of that, sorry, but that's how we work through it by hand. Not the way we want to do it when we get to a 3D large geometric object, right? Because this is just 3 elements instead of 10,000. Okay? So, for homework, work on the rest of the problems in the end of chapter 1.